This is problem 6-85. It's on page 320. A geothermal power plant uses geothermal water extracted at 150 Celsius at a rate of 210 kilograms per second as the heat source and produces 8,000 kilowatts of net power. The geothermal water leaves the plant at 90 degrees Celsius. If the environment temperature is 25 degrees Celsius, determine A, the actual thermal efficiency, B, the maximum possible thermal efficiency, and C, the actual rate of heat rejection from this power plant. Okay, so essentially what we've got here is a power plant that has a thermal source at 150 degrees Celsius. So thermal energy is extracted from this source to drive a heat engine, which they say produces 8 megawatts of power, so that's the power flow rate out. And the mass flow rate of geothermal water is 210 kilograms per second. Okay? Now, the geothermal water actually leaves at 90 degrees Celsius. Okay? So the actual TL, if you want to call it that, is 90 degrees Celsius, but the environment is at 25 degrees Celsius. Okay, so let's just leave that there for now. That's fine. Okay, and so we're supposed to find the actual thermal efficiency, the maximum, and then also the actual rate of heat rejection. So let's call this T sub L actual. Okay. All right. The solution I wrote out is from the last edition, so rather than going through that, I'll just solve the problem and then I'll rewrite it and post it eventually. But anyway, so let me start off by going for part B rather than part A or part C. Not that it really matters, but part B is a very simple one. Part B, the idea is, what's the maximum efficiency you can get? Well, that would be the Carnot efficiency. That would be a reversible efficiency, which is 1 minus TL over TH. Okay, the source that we're working from has a low temperature of 25 degrees Celsius. Now that's not good enough. We can't just take 25 over TH where TH is 150 because we have to plug in absolute units. So let's see, 150 and 273 are 423 Kelvin for the high temperature. 25 and 273 are 298 Kelvin for the low temperature. So that's what we actually have to plug in order to come up with the maximum thermal efficiency. So TL 298, TH 423. When you plug that in your calculator, you find the maximum efficiency. Yes, I need to do it too. 23. Actual efficiency, or maximum efficiency, is 29.55%, or so. I rounded it off a bit. Okay, so there's the best we could ever hope for any power plant to accomplish. Now, let's think about this. Let's see. I'm trying to think of a better way to do this. If because the way I did it before always confuses students. The actual heat transfer rate from the geothermal water can be computed, right? Q dot H is actually the mass flow rate of that water times the enthalpy change. So let's say H high minus H low. Okay, now normally what you would do, since we're talking about geothermal water, we're just talking about a temperature change. There's a lot left in this problem that the author doesn't make clear. For example, when the geothermal water comes out, does it come out as steam? Does it come out as liquid? That's not really clear. There are sources of geothermal water where it's so hot that it comes out of the ground as steam once you've relieved the pressure off of it. So I'm going to make an assumption here and say that he's just talking about liquid water coming out of the ground at 150 Celsius. If that's the case, then the only energy I need to consider this water giving me is just the sensible energy. Okay, so the temperature change energy, not a phase change energy. So I'm going to approximate this SCP delta T, TH minus TL. And since this is the actual heat transfer rate, since I'm trying to get the actual efficiency, then I should be able to come up with the actual efficiency. So, and I have to use the actual temperature here as well. Anyway, so the mass flow rate, 210 kilograms per second. The heat capacity of the water at constant pressure is about 4.18 kilojoules per kilogram per Kelvin. High temperature, 423. Low temperature, 298. Could have used Celsius there, it doesn't really matter. Okay. So here's the actual power flow rate in kilowatts that's coming out of the water. So let's see what number we've got here. 210 times 4.18 times, let's see, the difference between these two you can see is just 125. So times 125. This is 109,725 kilojoules per second, or in other words, kilowatts. So this is almost 110 kilowatts. Now, another version of this, if you will, if we change it to megawatts instead, this would be about 109 megawatts. Okay, so that's the actual power coming out of the geothermal water. And so if we calculate the efficiency now, the efficiency is just the desired output, which is the power output, over the heat input. Okay, so just 8 megawatts divided by 109 or so megawatts. You see the megawatts go away. I've still got the 109,725, so I'm just going to invert that on my calculator and multiply it by 8,000, because I've got kilowatts here, so I may as well convert the 8 to kilowatts as well. And that comes out to an efficiency of 7.29%. You can look at that and say, well, that's a horrible efficiency. Yeah, it's not very good, but remember that the limiting factor for a heat engine is the separation in temperature between the high and low temperature reservoirs. This is not a huge separation. That's only 125 degree separation. This is actually pretty impressive for that kind of difference. Now, I know the best we could ever do is about 30%, but we're probably not even going to get close to that. So this is probably doing fairly well. There are applications for geothermal water that's at high temperature, especially out west, where it's used for heating. So instead of converting the form of energy from thermal into work, what they'll do is they'll just use it directly to heat their homes or their businesses or whatever. You pull it out of the ground, it's at high temperature, just use it to heat in the wintertime. So that works very well. But there's some concern about it and whether drilling into these areas under high pressure actually cause earthquakes and things. Who knows? I don't know my area. But from an energy transfer standpoint, pulling that water out of the ground and using it to do this is a much worse idea than simply using it to heat the home, because you wouldn't have to pull as much out. If you use this to drive a heat pump even or something, it's not going to be as efficient as simply using the thermal energy directly to heat the home or business or whatever it is. So anyway, we've calculated the actual efficiency as well as the reversible or maximum efficiency, and the actual 7.29% efficient. How about the actual heat rejection rate? Well, they were actually asking for the rate, and I forgot the dot. Well, that's just going to be the difference, right? Q dot L plus W dot is equal to Q dot H. In other words, whatever thermal energy flows into the heat engine and does not leave as work or as thermal energy can't exist, right? I mean, it doesn't make any sense. It has to go one of these ways. So I guess I should say it this way. Thermal energy that comes in and does not leave as heat must leave, or does not leave as work, must leave as heat. So the sum of these two outputs here is just the input because of an energy balance around the heat engine. So we can calculate Q dot L, it's pretty easy. It's just the rate at which energy, or thermal energy enters the system, in the form of heat, less the rate at which work comes out. So that's just 109, let's just say, well, let's keep the whole thing. 725 less 8,000, this is of course kilowatts for both of these. And the difference between those two, you can calculate in your head, 101,725 kilowatts, or about 102 megawatts or so. So there's the actual heat rejection rate. I'll just write it down as 102 megawatts. Okay, that's approximate, but that's close enough. So there's the solution to this problem. Now there's just no way to do any better than 29.5%, at least as far as thermodynamics knows. So, no one, as far as I know, has ever seen this broken. If they have, I think that our energy production systems would be very different. And this is one of those limits that you run up against. That's from first principles. The general public doesn't know about it, and they don't know why you can't, make a car that can get infinite miles per gallon. How come we even need gasoline? Well, energy's conserved. That's why. So, anyway. One of the things I want you to get out of these problems and out of this course is the idea that the more times you convert energy, the worse it is, most of the time. Okay, so, like I said, if we're pulling this water out of the ground and it's hot, let's use it as thermal energy. Why convert it to work? That's not really what we need. If you can use energy in the form where it already exists, you're doing better.